Dang.
Alright, The Physics of Hollywood Movies by Chloe, Sarah, and Emma. Alright, so first we did Inside Out, Bing Bong's death scene. Okay, so we chose to look at it from momentum, energy, and kinematics. So when we first watched it, we didn't think that the momentum, like it followed the law of conservation of momentum. Because basically when they're in this wagon together earlier in the video, they don't make it all the way up, but then as soon as he jumps out, they do, like she makes it up by herself. So we use mv equals mv plus mv to do after the collision being when he jumped out. So we calculated time with a stopwatch, just like watching the video, and we based the distances all off the length of the wagon. So we figured out, we got this wagon in the back there as our like model, and that wagon's a foot long, so we based all of our distances off of that, and also the masses off of that. And then the mass of the broom was found online. We found like the mass of a broom on Amazon, and then scaled it down according to the size of the wagon. And we used Tinkerbell as the mass of joy, and we used Grand Canyon, like the height of the Grand Canyon, as the height of the canyon they were trying to escape from. And then we solved for velocity after Bing Bong left the wagon, basically. And the velocity was way too low. So basically we took that velocity and we used it here. We found that it was too low. So in energy we used 1/2 mv squared equals mgh to find the amount of energy they had when they were going up the ramp and the amount of energy she would have had like at the top of her projectile. And we figured out she only would have made it about 2 meters in the air. Grand Canyon is over 2,000 meters tall, so she would not have made it all the way up going that speed. And then we also used kinematics. We figured out even if she could have made it all the way up, how long would it have taken her? So we used d equals v naught t plus 1/2 at squared to figure out her, what the time would have taken for the whole flight. And we found out it would have taken her 22.3 seconds, but in the video it only took her 11. So Inside Out did not accurately portray any of the physics concepts we looked into. We determined the speed Joy was traveling was 6.447 meters per second, and she would have only reached a height of 2.14 meters with that speed, so she would not have been able to reach the top of the cliff. And also, if she could have even reached the height, it would have taken her about half the amount of time it did in the movie.
So our next scene was from Tangled. So for this scene we looked at kinematics, force, and pressure. So we didn't think that the horse would stay in the air for as long as he did. We also wanted to prove that the tiles would shatter in the same way they did in the scene, and that we thought that the horse's bone would break after he collided with the tiles. So for kinematics, we used x equals v naught t plus 1/2 at squared to solve for the time it took Maximus, the horse, to get from the castle to the roof of the house. So we approximated the distance between the castle and roof based on Maximus's body length. So for force, we used FMA, and the masses of Flynn Rider and Maximus were found online. And Maximus was modeled after an Andalusian horse, so we used that type of breed of horse's weight to get Maximus's weight. And then for pressure, we use force over area. So height of Andalusian at Withers was used to find the area of the 2 hooves. Pressure turn constant could handle was found online. And then we've discovered that the horse hock, which is like behind their like knee bone, is analogous to the human femur. So we use that human bone can withstand like 4,000 newtons of force. So we just said that a horse hock could withstand the same. So the circumference of the extra large horse hock was found online. And then we found that the horse hawk can handle 108,933,000 pascals. For the most part, Tangled showed evidence of accurate physics. Maximus's hawk would withstand the pressure exerted from the tile onto his leg. Horse hawk can withstand 108,933,000 pascals. 80,000 pascals were exerted on Maximus. And terracotta roof tiles were shattered after Maximus lands on the roof. Terracotta roof can withstand 957 pascals, while 80,000 pascals were exerted on the tile. The only difference was the time it took for Maximus and Flynn to get from the council to the terracotta roof of the house. We calculated to take 5.24 seconds in kinematics, but when timing it only took 3.5.
Okay, so the next scene is the saving Letty scene from Fast and Furious 6. Okay, you can stop it. Okay. I think that's possible. Okay, so the three main concepts that I focused on for this film scene was momentum, pressure, and kinematics. Yeah. So for the momentum, we use mv plus mv equals mv after, as well as v equals c over t. So the masses of both of the actors, Dom and Letty, were found online, and we used the distance of an average car lane, traffic lane, and multiplied by 1.5 to give the distance between the bridge, because that was just the proportion that was shown in the movie. And then we divided that by 2 because they met halfway between the bridge, and the time was taken from the video. And then for pressure, I used Vermont, and pressure equals force over area. And so I searched online a 1970 Dodge Charger length and width of a windshield because that was the car that they landed on at the end. Oh, sorry. Okay, so then for kinematics, we use more formulas. So V cosine theta for the x velocity, and V sine theta for the y velocity, and then V equals V naught plus AT, and then x equals x naught plus V naught t plus 1/2 AT squared. So the angle was found by copying the angle directly off of the screen onto a sheet of paper, and then used a protractor to find that angle, which ended up being 21 degrees. And then the V was used from the momentum calculations that I made at the beginning, and then the formulas were used to calculate time and final distance in the x direction. And then we compared the distance found to the distance that it would take to cross the bridge entirely. So based on the calculations, 2 parts of that scene were accurate. Were not accurate, and 1 part could have been accurate. So due to the momentum of the collision, the final velocity that they would have calculated was 0.4676 meters per second. However, in the scene, they continued moving at 0.9125 meters per second. Therefore, they weren't conserving momentum throughout. And then based on kinematics, Dom could have only traveled around 6 centimeters if he had gone off at that speed. But in the film, he travels at around 5.5 meters to make it across the bridge. So it's pretty impossible for him to have made it that far. However, for the pressure calculations that we found, using the measurements of the windshield that I mentioned before, the pressure landing on the windshield would have been 1,279 pascals, and the pressure needed to break a windshield entirely would be 275,000 pascals. So if that's the case, then they wouldn't have broken the windshield, and since that's only around 1,000, that's 275,000, the windshield may not have even cracked at all. So yeah.
Basically, the stuff we found online says it's really, really hard to break a windshield entirely, but not that hard to just crack it. But it isn't obvious what kind of pressure it takes to crack a windshield because it just depends so much on the temperature and everything else. Yeah.
Little pebbles crack windshields.
Well,
So
if they
it's
hit it
also
right,
how
yeah.
the sharper edges and stuff. That's also the thing. It's about the way that they would have landed on it. Maybe if he was wearing something that could have punctured it or something. But if you
Yeah, it
let
doesn't
your
have
entire
that.
body out, yeah, something like that, or a belt buckle or something. I don't know.
Yeah, that was sort of inconclusive. inconclusive, but we know that it wouldn't have like broken it completely. They wouldn't have fallen straight through into the car, which they didn't in the video.
Oh man.
I love getting some food. Phineas and Ferb is so good.
Welcome to Mr. Slushy Burger. May I take your order?
Anyone want fries?
Okay, so we focus directly on the part where they go down onto the
Oh,
tree.
let's look.
And they go onto the tree and they're like, anybody want some fries? So that tree is a big tree and it bends pretty much all the way to the ground. So Chloe and I did a little demo for you to show that that just can't happen.
You use the same music for every video.
That was our tree. That's like the same tree as Okay.
People must have thought you were so weird going on a time.
I have a question. How is like a person pushing on the tree analogous to like the weight of a whole
So-
roller coaster falling?
Yeah,
down the
so
tree?
we basically were trying to do that more with the sticks, was like showing more accurate like comparison of like the force going onto the tree, because like a person versus a stick and a roller coaster versus a tree, proportional.
And basically the biggest part of it is showing that like wood can't bend like that all the way down. It'll just break before it gets there.
Yeah.
Like if even if a roller coaster could exert that much force to bring your shit all the way down, it would snap before the tip of it hit the ground.
Yeah. Like in the first place it can't bend that far, and then second place, if it were to, it would break
Yeah.
by the time it hits that distance.
You guys are so smart.
I know. We hope you liked our demo. We have another one though.
Oh wait, where's the okay. This is from a movie called Speed. Basically the backstory of the movie is the two main characters are driving a bus and they can't go below 50 miles per hour or else a bomb that's on the bus will explode. And they're on a bridge going towards like a big gap in the bridge, but they can't stop or turn around because the bomb would go off. So their only choice is to try and go over the gap. And as you can see there is no ramp. They're going off at a horizontal angle. Remember that. Being launched horizontally.
What?
Sure, that makes sense.
So we're now going to prove to you that gravity exists. It basically looks like gravity isn't affecting the bus in this scene, but in real life it does. So basically, no matter how big or small the like object or vehicle is, it goes down. Even when it's bigger, it can't make it all the way across because immediately when it loses contact with the ground, it's launched horizontally. So it has 0 vertical velocity, and its only acceleration is negative 9.8 meters per second downwards. It's never going to have a vertical velocity, and it's always going to have a downward velocity as soon as it leaves the surface.